I'd like to talk to you a little bit about the geometry involved with vectors. In particular, I want to introduce a couple of concepts to you. One is the dot product of two vectors, which computes, in some sense, the projection of one vector onto another. And then the second thing that I'd like to do, which is more of a calculus idea, is to talk about the derivative and integral of vector quantities. Okay. Let's talk dot product. You'll notice that when we did vector algebra yesterday, we did not address the question of multiplying one vector by another. And the reason, there are actually a couple of reasons for that. One reason that we did not address that question is that there might be more than one way to multiply two vectors together. And in fact, that turns out to be the case. We're going to introduce the idea of a dot product, which sometimes goes by the confusing name of scalar product because it produces a scalar. But we're going to call it a dot product here. The dot product, W times V, is going to be equal to the sum of the products of the components of W and V. If we have more components, then we would continue to add on out. So, for example, if V is equal to 1, 3, and W is equal to negative 1, 2, then V dot W is going to be equal to the sum of the product of the x's plus the product of the y's. Or in other words, negative 1 plus 6, which is 5. Now, the very interesting question is, what's the significance of our dot product? But before we get there, I want you to observe that our dot product gives us a scalar quantity. We multiplied two vectors together, and we got some number here that's going to measure something about V and W. So the result of the dot product is a scalar. It has no components. It has no direction. Now, I want you to observe some things about our dot product. The first is that it is commutative. And I'd like for you to take a moment, just pause this recording right here, and see if you can prove that this property is in fact correct. Welcome back. If you cheated and didn't pause to try to prove it, pause it right now and try to prove it. Welcome back. So, if I compute V dot W, then I get this. If I compute W dot V, then I get this. And because scalar multiplication is commutative, I can immediately rearrange the terms like so, and look at what I get. I get exactly V dot W. So it's a pretty short step to proving that dot product is commutative. What else can we have? Well, we have a distributive property. We have a distributive property. Pause here and try to prove that for yourself. And welcome back. I will leave the details to your imagination. Hopefully it's already written down. We do not have an associative property. Why not? The reason we don't have an associative property is very, very interesting. This is a scalar. And so it is going to, let's call that scalar something like lambda. And so it is going to take the vector u and it's going to stretch it by some factor lambda. Meanwhile, this is a scalar also. Let's call it mu. And it's going to take the vector v and it's going to stretch it by a factor of mu. So that this quantity on the left here has a completely different direction from this quantity on the right here. So there is no associative property for the dot product. And this may be the very first instance of anything in math where you found a multiplication that was not associative. So I want you to pay close attention to it. Let's see. Another very interesting thing about the dot product is what happens when v dot w is equal to 0. I'd like to take a look at that for just a moment. When v dot w is equal to 0, what that means is that if we take v and w to be vectors with two components, vectors in two space, here's what this means. This means that vx wx is equal but opposite to vy plus vy times wy. And if I do a little bit of dividing of both sides by the x components, actually, let me sort out the v's from the x's. Then on this side, the ratio vy over vx is the slope of the vector v in two dimensions. And likewise, wy over wx is the reciprocal of the slope. Make this, let me put w on the same graph so you can see it a little better. So that wy over wx is the reciprocal of the slope of w. So what is this equation really saying? This equation is really saying that the slope of v is the reciprocal, the negative reciprocal of the slope of w. Oh, in other words, v and w are perpendicular to each other. Or in vector speak, we're going to say that they are orthogonal. Now what's cool about this definition here is that the idea of orthogonality now extends to as many dimensions as you wish. If you have two vectors in any dimensional space and their dot product is 0, then we say that those vectors are orthogonal to each other. They hit at right angles, which is pretty cool. Take just a moment to prove for yourself that the 0 vector is orthogonal to any vector. Okay, so with that in mind, we now ask a really interesting question, which is, what is the meaning of our dot product? And to get at that geometrical meaning, I want to observe something really cool, and that is that the dot product of a vector v with itself is exactly equal to the square of its magnitude. Is that so? Yeah, let's try it. That's going to be vx plus Vy which is equal to Vx squared plus Vy squared, which is exactly equal to the size of V squared. Okay. Now, to get in a more general meaning of V dot W, I want to consider a triangle that is formed by the vectors V and W. And if I form a triangle with the vectors V and W, both of them placed, we call it tail to tail, like so, and if I now connect from here to here, you can see pretty easily that this vector is W minus V. And you can see that because if I add V to this vector right here, which I've called W minus V, then what I get is the vector W, just like that. So we have a nice little triangle. And now what I'd like to do is I'd like to compute the size of W minus V in two different ways. First of all, I'm going to compute the size of W minus V squared. That's really what I'm going to compute here, by using the relationship that we just talked about. The size of W minus V squared is W minus V dot W minus V. And if we now simplify this a little bit, using our distributive property twice, so that we get W dot W minus V dot W minus W dot V plus V dot V. Then the first term here is the size of W squared. The second term here is the size of V squared. And these two terms right here, careful, they don't cancel, because of the commutative property, are actually the same, so that I get 2 minus 2 V dot W. And so we have, I'm missing a square right here. We have the size of W minus V, quantity squared, is this expression right here. Okay, so that's kind of cool. That's with vectors. Now I'm going to come back and do the same thing, but with a little bit of trigonometry. Because you all remember from trigonometry the law of cosines. And the law of cosines states that if I have any triangle with sides, let's say V and W, and call that C, and call this the angle between V and W, that C squared is equal to V squared plus W squared minus 2VW cosine of the angle between. If I apply that to this particular triangle, then I get that the size of W minus V squared is equal to W squared plus V squared minus 2 size of W, size of V, times the cosine of the angle between V and W, just like that. Well, you can totally see where this is going. If I set these two equal to each other, which takes me a lot longer to write down than it does for you to think it, then I'm going to get some glorious cancellations. This goes, that goes, the factors of -2 go, and what's left behind is a significance or geometrical meaning for the dot product, and that is that V times W is the size of V times the size of W times the cosine of the angle between the two vectors. And this immediately leads us to all sorts of cool things. For example, I can compute the angle between any two vectors now. Because the cosine of the angle between any two vectors is equal to their dot product divided by their sizes. which is just really pretty awesome. So for example, going back to the two vectors that started it all, for example, on the previous page it was. Yes, on the previous page here, we've got v equals 1, 3, and w is negative 1, 2. And so I can now compute their angle with the relation cosine theta is equal to dot product over sizes. And the dot product is 1 times negative 1 plus 3 times 2, or 5, over, and the size of v is going to be the square root of 1 squared plus 3 squared is 10, and the size of w is going to be the square root of negative 1 squared plus 2 squared is 5. So that when the dust settles here, I get 5 over root 50, which simplifies in a very delightful way to 1 over root 2. And oh, look at that. That just happens to be a special angle. So that we discover something about v and w that was not obvious from the original given definitions. And that is that v that goes over 1 and up 3, and w that goes back 1 and up 2, these two vectors are at a 45-degree angle with each other. How cool is that? We can also justify the use of the word orthogonal, because if v is orthogonal to w, and yes, we use the perpendicular sign for orthogonal, then their angle between them is 90 degrees. Excuse me. Which means that their dot product, v dot w, should equal the size of v times the size of w times the cosine of the angle between, and the cosine of 90 degrees is 0. And in fact, this is a bijection. I mean, not a bijection, is a biconditional, because if v dot w is equal to 0, then either v has to be 0, or w has to be 0, or the cosine of the angle between has to be 0. And if the cosine of the angle between is 0, then the angle itself is 90 degrees. So we have a really nice relationship, and the significance of the dot product is captured in its geometric form. So I'll write it one more time for you to think about. Later on, probably after we're all done this year, we will come back and use this to get some more very interesting features. I want to talk about a little bit more about the picture of the dot product. If I have v and I have w like so, then if this is the angle theta between them, this portion right here, we can think of v as being made up of two components, and one of those components is going to be parallel to w, and one of those components is going to be perpendicular to w. V parallel and v perpendicular. And you can see from the geometry that v parallel divided by v is equal to the cosine of the angle between those two vectors. So that v parallel is exactly equal to v times the cosine of the angle. Let me be proper here and put in my magnitude signs so that it's clear that I'm talking about sizes. Well, this is interesting because this fragment appears right here in this expression, so that I can immediately say that v parallel is also equal to v dot w over the size of w. And we call this the scalar projection I'm out of room. Here we go. size of V parallel is equal to V dot W over W is the scalar projection of V onto W. And here's the meaning of it. If you imagine a really strong light source coming from above that is shining directly over V here, then what this V parallel is, or VW is the shadow that V casts onto W. Now here's why we care about this. In physics and in some other places, we have work, we have need for these, because in physics we have work is equal to force times distance. But if my force and my distance are vectors that go in different directions, then the force is not fully efficient. It is only the component of force that is parallel to the delta x that actually does any useful work. And so to use this formula properly, what we really need is F parallel times delta x. But if you work that out, F parallel times delta x is going to be F dot delta x as vectors divided by the size of delta x. And now we're going to multiply that by the size of delta x so that these cancel. And the work done by a force is exactly equal to force dot displacement. This is the official physics definition. But of course, I never really had the opportunity to share that with my physics students. Well, very quickly, I want to talk a little bit about calculus and the derivatives and integrals of vector value functions. Imagine that I have a position, let's call it S, so we don't get confused with x and y components. A position that is a function of time. And here I'm going to use the I and J notation to express my components. We would say that this is the x component, of course, and then that would be the y component. So for example, we might have S of t is equal to t times I plus t squared times j. Or we might have something like S of t is equal to 3I minus 4.9 t squared j. If you examine what this is talking about, this guy right here, what this is really saying is that I have a position vector for every time t. So when t is equal to 0, my s is equal to 3. When t is equal to 1, my s is equal to, when t is equal to 0, my s is equal to 3 comma 0. Sorry, I got a little confused there. And the meaning of that position vector is the displacement from the origin, right there. When t is equal to 1, my position is 3 comma negative 4.9. There's the position vector right there. And when t is 2, my position is 3 comma negative something really big. It's close to negative 20. And you can see what's happening is that this is now describing the motion of a particle that is in the process of falling. And so we have described the motion of this particle in terms of a parameter t, which usually stands for time. We're going to have a lot more to say about parametrics when you come back on Monday. But here, I just want to introduce the concept of a vector valued function and what its derivative might mean. If I take the derivative s prime of t, then that should be the limit as h goes to 0 of s of t plus h minus s of t, and all of that divided by h. Keep in mind that this is a vector valued quantity. And if I now split up my components, my s into components, so that I have x I plus y j we're out of give ourselves a little bit more room here. There we go. Make our scribbles a little bit less problematic. And all of this over h. Algebraically, you can see what happens. I have two components that are horizontal because they are multiplied by I, and I have two components that are vertical because they are multiplied by j. Don't let the x's and the y's fool you. It's really the i's and the j's that determine direction. So that when I group like terms, something lovely happens. Plus the limit as h goes to 0 of y of t plus h minus y of t j, and all of that over h. But now you can see that all of this right here is simply the derivative of x with respect to time. And all of this right here is the derivative of y with respect to time. So that if s is equal to xi plus yj, then s prime is equal to x prime I plus y prime j. In other words, we can take derivatives term at a time, which is really nice. Component at a time, really. Well, what's the picture that we've got here? Well, imagine a particle going kind of all over the place. So he goes from here to here, starts here at t equals 0, and he stops here at some other time. And at each point, his position can be thought of as a vector from the origin, so that this is the vector s of t. And if we now go out to a slightly different position, s of t plus h, then you can see that as h goes to 0, s of t plus h is going to go to s of t. And the resulting vector that we get here, imagine this point sliding along the curve like so, the resulting vector that we get here is going to be tangent to the curve. So that we have the big geometric result, s prime of t is tangent to s of t at each t. And that's pretty cool. We'll have more to say about that with regard to parametrics. Well, our final thing is integration. And because s prime of t is equal to x prime I plus y prime j, it immediately follows that we can also integrate term at a time. That s of t is simply going to be the antiderivative of x prime I plus y prime j plus an obligatory constant vector c, which is going to be cxi plus cyj. And the integration happens factor at a time, just as you would integrate. The integration happens component at a time, just as you would integrate term at a time with regard to functions of x. This is a very, very